Hello everyone, welcome back to our playlist. In this video we will exploring the overvoltage and undervoltage protection, which commonly known as 59 and 27 in the ANSI code of protection. So this protection plays a vital role in maintaining the safe and reliable operation of the generators and their connected systems. So mainly the overvoltage protection helps to prevent the insulation damage and overexcitation, while the undervoltage protection protects the connected loads and auxiliary systems during the low voltage condition. We will look at how each function operates, their typical setting, and how to test and verify them using the OMICRON Test Universe module. So let's get started and see how the voltage protection ensures the stability and reliability in the power generation systems. So as you can see, the overvoltage protection, which is known as 59 in the ANSI code, is designed to protect the generators and its connected equipment from the excessive voltage conditions. So it prevents the insulation damage both when the machine is online or offline. In the phase voltage mode, as you can see, each phase operates independently, while in the positive sequence mode, the relay compares the calculated positive sequence voltage to defined set point. The overvoltage protection is particularly important in hydropower plants, for example, where a sudden loss of load can cause the overspeed and a dangerous voltage rise due to the slower response of the turbine governor. Typically, a two-stage protection scheme is applied, as the first stage operates at about 1.2 times the nominal voltage with a longer delay time, normally longer than the operating time of the voltage regulator, such as 5 seconds, for example, allowing time for the voltage regulator to act, and the second stage operates at around 1.35 times nominal voltage with a shorter delay of 0.5 seconds for faster tripping. In addition to protecting the stator insulation and transformer against overexcitation, the overvoltage function can also provide alarm signals to warn of rising voltage levels before they reach critical limits. So in summary, the overvoltage protection is used to protect the stator against unacceptable insulation stress, as well as the transformer against overexcitation. So the overvoltage protection is also used for alarm purposes in addition to the V over F protection, because an excessive overvoltage can result in a proportional increase in the frequency where the V over F protection doesn't operate. So as explained in our example, the voltage protection function provides a two-stage under and over voltage protection. The under voltage protection function is primarily intended as a protection for the connected loads, while on the other hand, the purpose of the over voltage protection function is to avoid the stator insulation defects inside the generators. So you can see the settings from here. So we have the V under 89.3 voltage, and the time delay 5 seconds, and second stage second stage of undervoltage protection is 73.5 voltage with a trip time delay 0.5 seconds. So the first stage is alarm or warning, the second stage is trip. On the same way also, V greater, which is the overvoltage stage 1 protection setting, is equal to 120.8 volt with a warning time delay 5 seconds. The second stage, V double greater, for the overvoltage protection equal to 136.5 voltage with a trip time delay equal to 1 second. And also here is the different parameters or different setting and SEL generator protection relay. Now we will talk about the undervoltage protection. So the undervoltage protection, which is known as the 27 in the ANSI code of protection, is generally not required to protect the generator itself, since the low voltage condition doesn't cause a direct machine damage. However, it's often included as a catch-all or for use in a protection logic schemes. So the function can operate based on the phase-to-phase or phase-to-neutral or a positive sequence voltage measurement, but it must always be supervised by a fuse loss detection and precomposition to avoid false trips. So we have a two-stage protection setup is typically used. So the first stage to be set around 0.89 times the nominal voltage with a delay of about 5 seconds, as we explained in the first slide, and providing an alarm or a warning stage, while the second stage set near 0.73 times nominal voltage with a delay of about half second, so to initiate a trip if the voltage drops too low. So also it doesn't protect the generator directly. The undervoltage protection is essential for protecting the motors and the other connected loads to the auxiliary supply system, with a typical stability limit defined at around 70% of the nominal voltage. Now we will talk about the testing of the overvoltage protection, the backup value. So when testing the overvoltage protection or the V greater function, the main objective here is to verify the backup value and ensure the relay operates correctly according to its set points. So this can be done using the test universe ramping module to gradually increase the voltage until the relay picks up at the expected level. However, we must keep in mind that a certain protection function may overlap, such as the overexcitation protection or other voltage-related function, which can make testing some parameters more complex, even prevent the accurate verification. So before starting the test, it's important to check the local hardware configuration. So we need a 3 voltage output should be mapped as a phase to neutral voltage, and we need one binary input should be assigned for the start signal, and another binary input should be configured to receive the trip signal or the alarm signal, in this case from the V greater stage, or the trip signal from the V double greater stage. So during the test sequence, we need symmetrical voltage at a nominal frequency must be applied to ensure stable and consistent test results. So you can see here is the test module setting for the V greater overvoltage backup value. So we have 4 ramps. The first ramp, here is there is no need to assign a binary trigger, and we will inject the nominal value of the voltage. In the ramp number 2, we will use the start or the warning signal to be a trigger condition from 0 to 1 with a 1% tolerance plus or minus based on the relay technical specification. On the same way, also in the state or ramp number 3, we will see also the trigger condition to be used with the start or the warning signal from 1 to 0, because we will ramp down. And state number 4, we will inject also the nominal value again to reset all the overvoltage protection. So you can see here from the ramp states, the ramp 1, which have the nominal voltage, the ramp 2 to ramp up the voltage value to get the backup value, ramp 3 we will ramp down or decrease the voltage value to get the drop off value, and ramp 4 to reset the relay again. And here is the ramp assessment, as you can see, for ramp 2 and ramp 3. So ramp 2 we will get the overvoltage protection backup, and ramp 3 we will get the overvoltage protection drop off, and we can compare the actual value with the expected nominal value based on the tolerance, which is 1% in our case, and it will give you the assessment in the ramp assessment view. Also, you can get the calculated assessment, which is the drop off over the backup value, which is called a reset ratio, which is expected to be more than 95%. You can also get this calculated measurement based on the actual measurement in the ramp assessment view. Here is how to test the undervoltage protection, also the backup value, by using the ramping module, but also in the same way. So when testing the undervoltage protection or V under function, the goal is to verify that the relay is accurately detects and operates at the set undervoltage backup value. So this test can be carried out using the test universe ramping module by gradually reduce the voltage until the relay picks up as expected. Before performing this test, it's essential to ensure the local hardware configuration, as we explained, is correctly set up. We need 3 voltage output should be mapped as a phase neutral voltage. One binary input should be assigned for the start signal, and another binary input should be assigned for the trip signal of the V greater stage or V under stage. So additionally, the circuit breaker close command, in this case, circuit breaker close status signal, must be wired to a binary input of the protection relay. And during the test sequence, we need also a symmetrical voltage with a nominal frequency must be applied, and any blocking of the undervoltage protection should be disabled to ensure an accurate and valid test result. So we can see here from the test module setting for the V under backup value. So we have ramp 1 with the nominal value of the voltage. Ramp 2 we will use start contact from 0 to 1 to detect the backup value of the undervoltage protection. So we will ramp down the voltage, as you can see from the ramp view here. We will ramp down the voltage to get the backup value of the undervoltage protection, and on the other hand, in ramp 3 we will ramp up the voltage again to get the drop off value of the undervoltage protection. That's why we need the trigger condition to be start from 1 to 0. And also you can see here the ramp assessment, as we explained in the overvoltage protection. You can see the ramp assessment, and also you can see the calculated assessment, which is representing the reset ratio, which is equal to drop off over the backup value. Now we will talk about the testing the delay time of the V under or V over stage for the under and over voltage protection stage 1. So when testing the time delay of the under voltage protection and over voltage protection stage 1, the test universe state sequencer module is used to verify each stage operates within the configured delay setting. So before starting this test, we must to ensure the local hardware configuration is correct, as we explained. So we need also circuit breaker close signal should be wired to the binary input of the protection relay to avoid the undervoltage protection. So in this test sequencer module, each stage is tested sequentially. So the healthy state number 1 to 3, this test steps are used to safely reset all the commands after each test step. And also in the detailed view, as you can see from here, the signal labeled the generator circuit breaker high command or the circuit breaker close command can be used to disable the blocking of the undervoltage protection function for state number 1 and state number 2 to ensure accurate timing measurement for both stage. Also, in order to assess the trip times, the corresponding test report has to be defined in the measurement value. So simply state number 1 and 3 will representing the healthy states, as you can see, with a nominal voltage and with 2 seconds. Here is the time limit without any binary trigger required. On the other hand, on state number 2, we will inject the undervoltage protection, as you can see, with a time delay longer than the expected time delay. So 10 seconds is more than 5 seconds for sure. So we can inject double the expected trip time here to get the undervoltage protection trip time. And also in state number 4, after resetting the voltage protection here in state number 3, we can use the state number 4 for the overvoltage protection, as you can see, with double the expected trip time, and we will inject a value more than the set value, as you can see from here. Then you can get the trip times here for the V undervoltage protection, which is expected to have 0.5 second, and also the overvoltage protection was expected to have 1 second, as you can see. So you can define the time assessment in the state sequencer assessment view. Now we will talk about the second stage of the undervoltage protection, how to test the backup value. So if we have the both stage on the same binary input or the same binary output of the protection relay, so we need to use the pulse ramping module in this case. So while testing the undervoltage protection stage 2, the test universe pulse ramping module can be used to verify the fast tripping operation at deep voltage levels. So during this test, it's important to note that the overexcitation protection function, which operates based on the V over frequency ratio, could interfere with this result. So to prevent this, the frequency of the fault state should be set slightly above the tripping point of the under frequency stage. So typically by about 20 millihertz, as you can see from this screen of the faulty state. Also in the binary output, as you can see in the binary output view, the signal generator circuit breaker high command representing the circuit breaker close status can be used to disable the blocking of the undervoltage protection. So before starting the test, make sure that the binary output number 4 of the CMC test set is correctly wired to the corresponding binary input of the protection relay to allow a proper control and monitoring during the test. So you can see here the pulse ramping, as you can see the reset state and the fault state, and also you can see the pre-fault time is set to 5 seconds. The reset time is 1 second to allow the relay to go for the reset state, and the fault time to be more than the expected trip time, which is 0.5 seconds. So we can make it 750 millisecond. And you can see from here the reset state and the fault state. So there is no any binary trigger needed in the reset state, but we need a binary trigger with the trip contact from 0 to 1 with the fault state to allow to measure the backup value of the undervoltage protection stage 2. By the same way, also while testing the overvoltage protection, the V double greater stage of the overvoltage function, the pulse ramping test module also can be used to verify this pickup value and the tripping behavior at the higher voltage level. So during this test, we must again consider the influence of the overexcitation protection function, which operates based on the voltage over frequency ratio. So to prevent any unwanted operation of this function during this testing, the frequency for the fault state should be set slightly below the tripping point of the over frequency, as you can see from here in the faulty state, which is typically around 20 hertz lower than the over frequency stage. So this ensures that only the overvoltage protection responds. So in this case, there is no need to use the circuit breaker high command or circuit breaker close command, since it's only required when disabling the blocking of the undervoltage protection function. But here we are testing the overvoltage protection, so no need to simulate the circuit breaker close command. And by following these steps, we can accurately confirm the performance and the timing of the V double greater stage under controlled overvoltage protection. So as you can see, here is the fault state. We can make ramping up of the voltage until we get the pickup value of the second stage. Also, we have the reset time to be 1 second to allow the relay to be resetted or to go for the reset state, and the fault time to be more than the expected trip time, which is 1 second. So we can put it 1.2 second. And here is the trigger condition, which is the trip of the second stage to be changing from 0 to 1. Then you can get the nominal value as expected, and you can compare the actual value with the nominal value based on the tolerance, which is 1% in our case, in our relay 7UM Siemens relay, and you will get the assessment of this value. So now we will talk about testing the delay time of the V overvoltage protection and undervoltage protection, the 2 second stage. So when testing the time delay of V double under or double greater stage, the objective is to verify that the relay trips within the configured delay time for both undervoltage and overvoltage condition. So we can use a test sequencer module for this test, allowing the trip times of each stage to be tested one after the other. So before running the test, make sure that the hardware configuration is correct, as we explained. And this sequence includes several healthy steps to safely reset all commands from or after each stage. Also, in the detail view, as you can see here, we can use the signal labeled generator circuit breaker high command to represent circuit breaker close status, which can be used to disable the blocking of the undervoltage protection during the state number 1 or number 2. And finally, to evaluate the measured trip times, the detailed test report should be configured and generated from the measurement view. So simply we have state number 1 and state number 3 to be the healthy states with the nominal voltage and with a time limit equal to 2 seconds, and without any needed of the binary trigger. As you can see, it's only requires that timeout, which is set to 2 seconds. And in the state number 2, we can test the undervoltage protection stage 2, as you can see. So we can define the value of the voltage to be 0.95 of the set value, and the time limit to be double the time limit. So we are expecting 0.5 seconds, so we can put it 1 second, and the trigger condition here to be the trip from 0 to 1 to assess the undervoltage protection stage 2 trip time. Also, in the same way, for the state number 4, to test the overvoltage protection stage 2, we can define the overvoltage value to be 1.05 volts from the setting. So we can inject 82.75 volt with 2 seconds, because you are expecting 1 second, and we can define the time assessment, as you can see from here in the time assessment view. And here is the end of our video. Thank you, and stay tuned for the next video.